Welcome back to the module 3. We are continuing nonlinear effects which is generated due to the propagation of ultrafast pulse through the dielectric medium. So far we have discussed the many nonlinear effects, and in the previous lecture we have discussed third order nonlinear effect including transient grating and polarization getting. Those are third order processes. Now we will discuss higher order process including high harmonic generation. Most of the ultrafast laser sources synthesize ultrafast pulses with center wavelength at 800 nanometer. This is, we have already shown that the laser sources primarily depends on the tie-sapphire crystal, and tie-sapphire crystal can gives the emission at 800 nanometer, near 800 nanometer. That's why most of the laser system, ultrafast laser system produces this kind of 800 nanometer pulses. We have seen that nonlinear optical techniques play a pivotal role to further upshift or downshift light from 800 nanometer to different wavelengths. It can be, we can go to IR regime, we can go to X-ray regime with this nonlinear frequency conversion processes. Nonlinear frequency conversion techniques almost exclusively rely on crystalline solids as nonlinear medium. We have already seen that for efficient conversion, phase matching must be achieved, and this can be achieved by relying on anisotropic material. Birefringent crystal thickness also plays an important role. The reliance on solid state materials severely limits the application of nonlinear optical techniques to very short wavelength. We cannot create short wavelength, very short wavelength, less than 200 nanometer we cannot create in a crystal, because crystal will start absorbing those high energy photons. The best solid nonlinear material such as lanthanum, boron oxide and barium boron oxide can be used to generate light at wavelengths as short as 200 nanometer. Most of the solids are not transparent at wavelengths shorter than this. None are transparent in the extreme ultraviolet or X-ray regime of the electromagnetic spectrum. On the contrary, many gases are transparent well into vacuum ultraviolet, and even shorter wavelengths can propagate through the medium, through the gas medium with moderate absorption. This is why one can think of performing high harmonic conversion of 800 nanometer light into EUV, extreme ultraviolet regimes are shown here in a diluted gas medium. We shall see that high harmonic generation, HHG, in short is called HHG. This high harmonic generation in dilated gas medium provides a useful source of XUV or soft X-ray. High harmonic generation represents an extreme nonlinear process in which more than 10 or even 100 input photons from a visible or near infrared laser are combined together in a frequency of conversion process. So one can say that, okay, I have this, all these photons clubbed together of 800 nanometer. 800 nanometer is approximately 1.5 eV. So all these photons will be clubbed together, and I can create a big photon that is in X-ray regime. And this number can go up to NH nu, then NH nu, H nu, and nu is 1.5 eV H nu. This n number of photons which can be clubbed together, they can be of the order of, let's say, 100. This n can be 100, n can be even 1000. So this is an extreme nonlinear process where It is not third order, fourth order, it is going to be hundredth order or 2000th order. So this kind of high order harmonics can be generated with the help of high harmonic generation process. HHG provides, high harmonic generation provides an attractive source of ultrafast pulses in the extreme ultraviolet and soft X-ray regime. When we derived 1D equation, one-dimensional equation for nonlinear optics, if we remember, this was the equation which we have driven. We have received this. We have got this equation. This was, so basically what was the picture we had in the derivation of the nonlinear propagation of the ultrafast pulses. We said that there is an input beam, then that is creating nonlinear polarization, and that nonlinear polarization is created emitted beam. Now question is how this induced polarization and emitted beam, they are connected. They are connected with the help of this equation. This is ZT one-dimensional problem, Z2 minus mu naught epsilon E, this is emitted beam, 2 equals mu naught 2p nonlinear polarization d to t. So this was the equation we got as a nonlinear equation of optics, and this equation was obtained assuming that the nonlinear polarization is weak, that is the perturbative limit. So we assume fairly weak nonlinear process, that is the perturbative limit is employed, which explained numerous nonlinear optical phenomena already. We have seen that phase matching particularly is one important factor which we have got from this equation. The conditions was obtained from this equation. And second harmonic generation we have seen, self phase modulation we have seen from this nonlinear optical processes, but those processes are lower order processes. For HHG process, this perturbative limit breaks down because of the extreme nonlinear nature of the process. As I have told you that it can be 100th harmonic we are generating. HHG occurs when an intense ultrafast pulse is focused into a noble gas medium such as helium, argon, etc., as depicted here. So I have a gas inlet and outlet. So it's going inside, and I have femtosecond laser pulses focused inside this gas medium. This can be fiber, this can be optical fiber, or this can be gas jet, or this can be gas cell. Once we focus that beam, then we create the X-ray at the focal point or near the focal point, focal region, and then we can filter the fundamental beam. We can use metallic filter, because we know that high frequency photons having higher penetration depth as compared to the low frequency photon. So that's why we can use aluminum filter or metallic filter, and then if we disperse the beam, we will be able to see the spectrum. And generally the spectrum, how does this spectrum look like, high harmonic generation spectrum? Typically it looks like this. This is the H nu photon, and this is the, let's say, intensity. It creates third order, then fifth order, then probably seventh order, then there is a plateau, and then suddenly there will be cutoff. So this looks like this. There will be a plateau regime. There is a lower order harmonics gradually decreasing quickly. That is third, fifth, and always odd harmonics will be produced. So this is your third, then this is fifth, this is seventh, then so on, blah blah, and then suddenly there will be a sharp cutoff in the spectrum. So that's the very common feature of the HHG spectrum which we can monitor. The required focus intensity of the fundamental beam, this fundamental beam focus intensity has to be at least 10 to the power 13 watt per centimeter square. Meaning of this 10 to the power 13 watt per centimeter square is now obvious. What does it mean? We know that this is the peak intensity. This is peak intensity. and we need very high peak intensity to obtain this high harmonic generation. Although the most accurate description of HHG process involves numerical solution of the nonlinear Schrodinger equation, a quasi-classical three-step model proposed by Corkum can also accurately predict the general feature of HHG. According to this model, as depicted here, in the first step, the intense laser field suppresses the Coulomb potential of the atom. So, this is the first step. When I have electron attached, so we'll express it. Let's say I have a nuclei and electron sitting together. Now, due to interaction of the strong laser field is, let's say, propagating along this direction, and when laser field is propagating along this direction, the field is changing its polarity along this direction. It's a perpendicular direction, and every half cycle is changing the direction. So what will happen, this field will exert force on the electron. So once tunnel ionization occurs due to strong field, this electron is free, and this electron is experiencing the electromagnetic wave which is propagating along through the medium. So now what will happen, due to this field, at a particular point this electron will be accelerated away from the atom, the parent ion, cation, and then after a certain time, which is half cycle of the optical cycle, after the half optical cycle, this electron will come back again because the polarity has changed and it will come back. And there is a possibility, the probability is very low, but there is a possibility that the electron will find its own parent cation or parent ion, and it will recombine. And when it will recombine, it will give the emission. So that's all about high harmonic generation process. It's a three-step process one can explain. The first step is tunnel ionization, which will make the electron free. Then electron will propagate along in the field, and that will acquire kinetic energy, and then they will recombine. This recombination step is the last step. When they will recombine, they will emit the field, and when their emission occurs, they will emit the ionization potential plus the kinetic energy it has gained when it was traveling in the field. So, so the first step, the intense laser field suppresses the Coulomb potential of the atom of the molecule, allowing tunnel ionization. The tunnel ionization process is something like this. So I have a Coulomb potential which is something like 1 by R. That's the Coulombic potential, and I have an electron here. So due to strong field, what might happen, this potential will be suppressed down to this, and suddenly this electron can be tunneled out, and I can have this free electron. That's called tunnel ionization process, which is the first step of HHG process. Second step involves evolution of the free electron in the laser field. As the optical field oscillates, it first propels the electron away from the ion, and then when the field reverses, the field accelerates the electron back towards the ion. Finally, the third step is recombination of the free electron with its parent ion, emitting high harmonic photon. The ionization and recombination can occur in every half cycle of the driving field. So if I consider the driving field instead of this one of cycle, I can now consider, we know that a pulse may have a number of cycles, and I can represent it like this way. So this is called carrier wave of the pulse, and it has a number of cycles, and in every half cycle I will produce this HHG, which means that here I'll produce HHG, here I'll produce HHG, here I'll produce HHG, here I'll produce HHG, and continuously I produce HHG pulses. Okay, each pulse is of the attosecond time scale, of the attosecond duration, but overall this pulse would be femtosecond, just like the parent beam. So in every optical half cycle, I will have a burst of electromagnetic energy. This is called the attosecond pulse train, but the overall total pulse duration of the XUV beam is going to be femtosecond. or same, almost same as the pulse duration of the driving laser field. This three-step model can be expressed analytically, and we'll look at the analytical expression. The real field, is represented by, let's say, E t equals E naught cos omega naught t. I'll consider this one. We are not considering pulse here because it is the each optical cycle which is important. That's why we are considering only the plane wave expression. Here we have considered that field does not depend on space coordinate. This is reasonable approximation as long as wavelength of the input beam is large compared to the atomic size. In addition, a few assumptions are employed. Electron was at rest in an atom before tunnel ionization. So this is the process we are considering. We are considering that it is coming back to x equals 0. Starting from x equals 0, it's moving away and then coming back to x equals 0. That's the trajectory of the electron. Electron was at rest in the atom before tunnel ionization. Electron was suddenly completely free. So there are few assumptions we have made here, is that electron at rest before tunnel ionization. Second assumption is that electron was suddenly completely free. Electron will face only electric field of the laser. Electric field of the parent ion is ignored. The electric field, after we have ionized it, electric field of parent ion is ignored, and electron is accelerated at time t equals 0, t equals t naught, from position x equals 0 along x axis. This is the acceleration. So these are the assumptions we have made. Under this assumption, the force experienced by the electron due to oscillating electric field is given by, so I had an electron here at this point and I want to know the force. So force is going to be m dv dt, which is nothing but minus e naught cos omega naught t. So if we have this, then we can integrate it and we can get velocity to be minus e naught by m omega naught sine omega naught t plus v naught. This is the velocity we get according to the assumption made above. Electrons was at rest at the time of ionization. So we can say that at t equals t naught, v equals 0. I can say that. And if we have this initial condition, then we have v naught equals e naught by m omega naught sine omega naught t naught. So we can insert that here and we get Vt is nothing but minus e naught by m. We get Vt equals minus e naught by m Vt equals minus e naught by m omega naught sine omega naught t naught, sine omega naught t plus E naught by m omega naught sine omega naught t naught. Similarly, we can integrate with respect to we can express this one as dx dt, and we can integrate, and when we integrate it within this limit at t equals t naught, we have x equals 0, and that is the initial condition. This is the boundary condition we employ. Then we get xt value also, which can be expressed as e naught divided by m omega naught square cos omega naught t plus e naught t divided by m omega naught sine omega naught t naught minus e naught divided by m omega naught square cos omega naught t naught minus e naught t naught divided by m omega naught sine omega naught t naught. This equation features the oscillatory trajectory of the electron in the input field. Now, this is the expression for the trajectory of the electron, which will follow under the assumption of following assumption. Assumption is that, first assumption is that t equals t naught at the initial time x equals 0, that is we started with x equals 0, and at t equals t naught velocity was also 0. That is also one more assumption we have taken. So with this assumption we get an expression for x. It is also assumed that at the time of recombination electron comes back to rest. If time taken by electron for acceleration and recombination is defined by tau, so if I express tau as t naught t, that is the time, this time of recombination, if I express as t naught plus tau, then this recombination occurs when x equals 0, then we can write down that following expression: e naught divided by m omega naught square cos omega naught t naught plus tau plus e naught t naught plus tau divided by m omega naught sine omega naught t naught minus e naught divided by m omega naught square cos omega naught t naught minus e naught t naught divided by m omega naught sine omega naught t naught equals 0. So we can now use this cos A plus B identity. This can be decomposed. Cos A plus B equals cos A cos B minus sin A sin B. We can use this identity and we can decompose it, and if we decompose it we will be able to cancel out few terms, and then we get this. We get following expression. One can do this derivation very easily. Cos, I'm going to write down this final expression, cos omega naught t naught multiplied by cos omega naught tau minus 1 minus sine omega naught t naught multiplied by sine omega naught tau minus tau omega naught equals 0. We get this expression. Or or we can write down this sine omega naught T naught divided by cos omega naught T naught equals cos omega naught tau minus 1 divided by sine omega naught tau minus tau omega naught. This is the expression we get, or this can be written as tan omega naught T naught equals this. So this will be useful, this expression will be useful to further reduce the expression, the kinetic energy expression, which we'll write down in the next slide. Now we shall go back to the equation which features electron trajectory to estimate final kinetic energy, because remember we are interested in IP plus kinetic energy, and we are interested in knowing the kinetic energy gained due to the external the electromagnetic field we have. IP is constant for a system. IP is the ionization potential. That is constant, we cannot change it for a system, but Ke should depend on the external electric field, and that's exactly what we are trying to calculate. So kinetic energy, E kinetic energy can be expressed as half m v square, and V has an expression. V is a function of T naught plus tau. So at the time of recombination, the time is T naught plus tau. I have to find out the kinetic energy, and that kinetic energy can be expressed as half m. Then I insert the expression for V, that is E naught divided by m omega naught, then sine omega naught T naught minus E naught divided by m omega naught, then sine omega naught T naught plus omega naught tau whole square. This was the expression for V at the time of recombination. So we can simplify this one further, and we can get this expression, and we can actually decompose this sine function as well, sine A cos A plus sine A cos B. So this trigonometric expression we can decompose, and finally I'm writing the final expression which we get is half then E square E naught square divided by m omega naught square multiplied by cos omega naught T naught multiplied by tan omega naught T naught, then multiplied by 1 minus cos omega naught tau minus sine omega naught tau cos omega naught T naught whole square. So this is the expression we get, and we remember tan omega naught T naught, we got an expression in the previous slide, so we should plug that in. The moment we plug that in, finally we get this expression, and we can simplify this expression further to get this expression, half E square E naught square divided by m omega naught square, then cos square omega naught T naught multiplied by minus 2 minus plus 2 cos omega naught tau plus tau omega naught sine omega naught tau divided by sine omega naught tau minus tau omega naught whole square. We get this expression, and if we perform trigonometric identities. We can use trigonometric identities to write down this final expression for Ek, that is the kinetic energy. One can do this math very easily. Half E square E naught square divided by m omega naught square, then 2 minus 2 cos omega naught tau minus tau omega naught, then sine omega naught tau square divided by 2 minus 2 tau omega naught sine omega naught tau plus tau square omega naught square minus 2 cos omega naught tau. So this is the expression we get, final expression for the kinetic energy at the time of recombination. So this kinetic energy will be added to the photon energy, emitted photon energy. Thus the above equation suggests that the final kinetic energy of the electron due to acceleration and recombination depends on total time taken due to acceleration and recombination. Now let us, so what we see here is that this expression depends only on tau. Tau is the time taken, total time taken for the acceleration and recombination. We do not have any T naught component in this expression. This expression depends only on tau, that is the total time taken for this. So basically, if I at this point, if I remove, this is actually x equals 0, if I remove an electron, this time, total time is tau, and final kinetic energy depends on this total time. What is the trajectory? If the trajectory is like this, is fine. Trajectory can, so different trajectory I can have. Although I am showing it with the lobe, but it is a one-dimensional problem we have solved, so it is actually going along x direction. Just but for visual clarity, I am showing it through the lobe, showing the trajectory going away and then coming back. Now we will derive an expression for the ponderomotive energy, that is UP, which is defined as the average kinetic energy. That's UP. Now I will define, that is defined as average kinetic energy, average kinetic energy gained by the electron if the electron, this is gained over an optical cycle, if the electron was assumed to be at rest in an atom, that is, we will consider V naught equals 0. So this is what we will consider. If V naught equals 0, in the previous expression we haven't said V naught to be 0. We said that initially we can have a velocity, but if the V naught is 0, then the average kinetic energy will be considered to be ponderomotive energy, and in that case ponderomotive energy UP can be expressed as half m 1 by capital T is the period. Integration is going to be T minus T by 2 from T plus T by 2. This is the integration limit, Vt whole square dt. This is the integration we want. So this 1 by T term, this is the average quantity determined to determine an average quantity over an optical cycle. This is the way we do this. And if we insert the Vt expression without V naught term, if the V naught term is removed, then I get only sine function, and I can write down this as half m half half e square E naught square divided by m omega naught square 1 by t, then t minus t by 2 and t plus t by 2 sine square omega naught t dt, which is nothing but 1 by 4 e square E naught square divided by m omega naught square. This is the and the average of sine square function over an optical cycle is going to be half. That's why we can take this integration as we can get the value like this: 1 by 4 is square E naught square divided by m omega naught square. So now if we see that this expression, the part of this expression is here, is present here in this. So we can plug that in and we can get that kinetic energy expression Ek, final kinetic energy expression Ek equals 2 up non-normative energy multiplied by whatever we have written here, this expression, whatever we have written here. So 2 up multiplied by this. So if we plot this Ek versus if we plot it, we'll plot this Ek by up. If we plot this Ek by up, then as a function of omega naught tau, if we plot that, then we get an expression, we get a plot like this, which will having a maxima, and this maxima will appear when this maxima will appear at the value of 3.17. This is a characteristic number, and that's why we can say that E kinetic energy maximum divided by up is going to be 3.17, or in other words we can write down that E kinetic energy maximum equals 3.17 into up, average kinetic energy gain in the acceleration process. So I get a maximum value of the kinetic energy. It cannot go beyond that. So the spectrum which we have previously proposed, that the spectrum looks like the spectrum looks like an odd harmonics coming down, and then there is a plateau, and then suddenly there is a sharp cutoff. This cutoff will be controlled by this E maximum kinetic energy, which is nothing but 3.17 up non-normative energy, 3.17 non-normative energy. As high harmony generation occurs in gas medium, which features an isotropic medium and has inversion symmetry, the PE function introduced early in this chapter gets odd symmetry. That PE function, that is polarization. So we said that we have a medium, and the polarization we create due to the input beam propagation through the medium. This is input beam, this is polarization, and we said that polarization has this form: epsilon naught 1e input plus epsilon naught 2 input square plus epsilon naught 3 input cube plus blah blah blah. Like this way we said that. Now because the medium we are using is a gas phase medium, it's an isotropic medium, it has an inversion symmetry. So in order to obtain this inversion symmetry in this PE function, I have to neglect this even terms. So in the end, due to this medium in the where the nonlinear polarization is created for the high harmonic generation, so PHAG polarization will depend only on the odd functions, that is E cube plus epsilon naught 5 e to the power n 5 plus blah blah blah. All odd harmonics will be created. So that's why when you plot the frequencies, we see that this is the spectrum we see generally, and and these peaks are representing odd harmonics only. So odd harmonics is generated due to the medium characteristics. With the h nu, HHG is nothing but IP plus kinetic energy, or maximum h nu. We have also seen there is a maximum of h nu which can be defined with respect to the maximum polymetric energy, which is nothing but IP plus 3.17 UP. That's the maximum energy we get. And if we want to extend this cutoff, if we want to extend to the higher frequency regime, then what we need to do, we need to change the polymetric energy. Polymetric energy will depend on I intensity as well as lambda naught square. So this is proportional to the intensity and lambda naught square. So both can be changed. These are the characteristics of the input beam. So for the input beam, if we increase the intensity, the polymetric energy can increase and the cutoff can increase. On the other hand, for the input beam, if I increase lambda naught, then also we can increase the cutoff. These are the very important characteristics of the HHG process. We'll stop here and we'll continue this HHG discussion in the next lecture.